So let's begin. How many of you went to our our lecture on isomorphic reasoning yesterday? Okay, roughly like half of you. Okay, so the first part is going to be sort of like an introduction to type algebra and isomorphisms all over again, but it's sort of a soft prerequisite for all of the rest of the talk, so we'll have to go through. And I guess my opening statement about this talk is that at our isomorphic reasoning lecture, I said that there are a lot of overhyped technologies, overhyped techniques in functional programming, right? And in this talk, I want to show that a lot of that is just the same idea over and over and over and over again, right? And so, how many of you have worked with recursion schemes? Okay. And what about final tagless? MTL. Free. What about like freer monads? I mean, I guess it's free as well, right? Yeah. Or like polysemy, or there's a whole, I'm not even sure how many free monad libraries there are in Haskell, but everybody seems to invent their own, right? And there is also F, which is roughly the same idea, except that maybe with slightly nicer syntax. Okay, so first we're going to go over type algebra. We'll need isomorphisms. We'll need basically isomorphisms are going to give us a way to transform our expressions and transform between two different but isomorphic representations of the same idea. And then we're going to talk about final tagless, initial encoding, just a little bit, and just in general about like what things are and how to think about different data structures and how to think about recursion. And then I'm going to introduce free for you, and also we'll talk about like different ways to represent free programs, and we'll discover that if you have a free program, you can convert it into a program written using MTL, using final tagless, using explicit dictionary passing, like many different ways. Unfortunately, if you are, I hope you are all familiar with Scala. If you are not familiar with Scala, well, Scala is a very simple language. And for the most part, all of the slides are going to map directly to Haskell, in the sense that I'm not using any crazy techniques. Okay, so isomorphisms. What is an isomorphism? An isomorphism is a bidirectional mapping between two types. And we're going to say types because in this particular case, we don't need any like category series, sets, anything like that. We only care about types. And so in our case, isomorphisms are just two functions. And two functions, one mapping from A to B, one mapping from B to A, such that their composition is identity in both directions. Now, this is not valid Scala. But this is what we would ideally write. Like Scala has singleton types, but it doesn't have, because it's not pure, and because it has like a lot of sort of functionality that is not exactly, pure and functional, we cannot really express it in Scala. And we cannot really express this type in Haskell either. But the idea is that basically what I'm saying there is that, well, I'm going to give you two functions from A to B, from B to A, and I'm going to give you proof that if you compose those functions in either direction, you're going to get an identity. But since we cannot express any proofs, we have to just manually verify that all of our isomorphisms are actually isomorphisms. So the first question is, like, ours is isomorphic. Those two types, A and B. Yes. The answer is yes, because there is an isomorphism. We can pattern match on either Boolean or unit. And for all of the cases, we can produce one case of the other ADT. What about this case? This one is a little bit trickier. But if you if you went to yesterday's talk, you know that yes. Well, it's like 2 to the power of 2, 4, and the other one also has 4. They must be isomorphic. But one way to think about it is that we have a table of, for every input value, we have one output value. And so a function can be represented or thought of as a giant tuple of where every component has type B, but there are a total of A values, right? For every single value of A, there's one entry. And here we constructed the isomorphism directly, explicitly. And basically what we do is, we convert our function into a table first, and then we see which of the possible tables it is. So, like first we supply it with true and false. That gives us all possible values of that function. And then we look at those and pattern match. Right? Does it make sense? Okay, good. Now, what about this case? Are they all isomorphic or not? Unit it's a singleton. In Scala, it's a singleton. So it's basically like in Haskell, you would write it as opening parenthesis, closing parenthesis.
I'm going back to your talk from yesterday.
Mm-hmm.
We're trying to figure out how many folds we can put in here. So what would you use for the first one?
Well, one way, at this point, I would probably just say, Boolean to unit is 1 to the power of 2. So, and immediately say that it's 1. Simply because I already know that there is such a mapping and it works. And therefore, So, the easy way to think about this is, consider just the tuple representation of both of those two functions. Right? The first one is going to have, it's going to be a tuple of 2 values of type unit. And there's only one value of that type. And the second one is going to be an empty tuple of ints. But since it's empty, there's also only one value. And the third one is just unit, so also one value. Now, if we construct the isomorphisms directly, we're going to discover that something really funky going on there, because we have to discard arguments in some cases, and we have to use absurdity in some other cases. It's kind of like, it's not immediately obvious how to construct this, and why there's only why there aren't many different ways to map, say, one to the other. So a different way of thinking about this, and comes. Yeah, let's look at first. Let's look at an example, right? I used the same example in the previous talk, so that's why some people are laughing. But basically, we have 3 different representations of the same number, and trust me, those are the same numbers, right? 12 to the power 3 plus 1, 17, 29, and the first number expressible as a sum of 2 cubes in 2 different ways, right? So are they equal? I mean, as values they are, right? But are they equal expressions? No. And so what we really care about is their properties, the things that we can tell. How can we tell them apart or not? Like in our code, can we tell them apart or not? If we cannot tell 2 things apart, then they're essentially equal. And so Leibniz came up with this principle, which I really, it's my favorite thing on Wikipedia. I constantly, like pretty much every week I open this page. Yeah, it often comes up. But it says that if 2 things are identical, then they have the same properties. And if 2 things have the same exact properties, then they are identical. And sort of like a philosophical principle. But we can apply it here. We're going to say that 2 things are equal if they have all the same properties. Now, if those 2 expressions are, well, expressions, then we can distinguish between them, right? Because we can observe the difference. We can pattern match, and we can see that one is addition, and the other one is a literal number. But if we discard that information, then we can no longer see the difference, right? Because here, there is no way to distinguish between those 2 expressions anymore. Like all of that information, the structure is lost. And so if we apply it here, what we need to do is to say, all right, let's say that somebody asks us to write a property that distinguishes between 2 functions going from Boolean to unit. How would we do that? Can we distinguish between those 2 functions? On top, the first 2. Right? The first one ignores its argument and returns a unit. The second one pattern matches on its argument and returns a unit. But there is no way to distinguish between those 2. Right? Like it doesn't matter what argument you pass in, both of them always are going to return a unit. Which means if there are no properties to distinguish them, that means that they are exactly the same. And in the second case, again, I have like 3 different, they look different, those 3 functions, right? One is returning 1, takes an argument and returns a 1. The other one returns a 2, and the third one returns just x. And it uses a subtyping relation between nothing and unit and int in Scala. But if I asked you to distinguish between them, you wouldn't be able to do that. Because in order to distinguish between them, you would need to pass an argument. And in this particular case, the argument is nothing. There are no inhabitants. And so, since we cannot see the difference, that means that they're equal values. They're identical according to this philosophical principle. If we can see the difference, if we represent them as expressions, then we can see the difference. And in which case, they are different values. They are not identical. And when writing code, we really care about properties that are expressible in our language, because that's what affects semantics. Now, there are certain other properties of code that you might be interested in, like performance. in which case equal expressions that are equal in your language might actually be different to you because you can observe other differences between them. So it's important to understand that all of this is relative to what kind of things you can see about your code. But in this lecture, we're going to be focusing exclusively on properties within our language. And so we find that both counting and identity of indiscernibles gives us the same result in this particular case, which is that both of those have only one inhabitant. Now, an interesting result about isomorphisms is that if you have an isomorphism between A and B, then equal values are going to map to equal values, and different values are going to map to different values. It's quite straightforward to prove. You just take two values. In A, you apply 2 to them, so convert them into values of type B. And as long as your equality is preserved by function application, then you end up with an equality on B's. And in the opposite direction, the same logic applies. All right. Now, there are quite a few useful isomorphisms that you can use. And we're not going to, in this talk, we're not going to prove any of those. So I hope that you can just take a look at them and see how you would do, how you would convert from one representation to the other. So for example, in the first case, we have a tuple of A and B. How do we convert it to a tuple of B and A? We just swap them, right? Now, if we replace either with a plus, tuple with a multiplication, unit with 1, and nothing with 0, we end up with something very familiar, right? What does it look like? Please, if you've been to, if you already know the answer, if you already knew the answer, do not raise a hand. Yes, it's yes. Fields also have very similar axioms, right? It's actually closer to a semi-ring or a power semi-ring because you can also take powers, as we'll see. And you could also say that it's pretty close to what we consider to be like natural numbers. And in fact, you can show that this mapping or correspondence is, works all the way, essentially. Like everything except negation and division map in both directions. Now, we'll need a couple more important results about functions, which is that we can carry them, and also that there is this pairing axiom, the first one. Those are pretty useful because they come up a lot when dealing with, well, pretty much anything. And here I called pairing like diag, I don't know why, but whatever. Okay, so is it clear why the first one is true? The first isomorphism is true. So basically the idea is that we have let's say we go in this direction, from this side to this side, right? We have a function that takes either A or B and returns a C. And we need to produce two functions. One takes an A and returns a C, and another takes a B and returns a C. In order to produce the first one, we take an A, right? We create like a lambda expression over here. And we pass left of A to this function. And similarly for the second one. And in the opposite direction, if we have two functions, right, we essentially like fold over this either, right? So we pattern match on either, we check if it's left, then we run the first function, otherwise the second function. So is everybody okay? Yeah.
So the _1 and _2 is essentially
First and second, if you're familiar with Haskell.
not really.
Okay, so then it's the first component of a tuple and the second component of a tuple.
Okay,
Yeah.
in what sense are those diagonal?
Yeah, that's a good question. It's just a name. Naming is hard, you know. But I think that the right, you know, like somebody told me that the right name is pairing, because you are pairing two functions together, essentially. Well, it turns out that similarly how tuples are multiplication and either is like addition on natural numbers, similarly functions are correspond to exponentiation. The only thing to remember is that exponentiation in the opposite order of the function type parameter. So a to b is b to the power of a. And you can see that both of those statements, the pairing and currying, correspond to very, you know, like things that we know about natural numbers as well, right? So we know that c to the power of a to the power of b is the same as c to the power of a multiplied by b. Okay, so this, we're going to be using a lot of like type algebra, and so I'm going to sort of simplify things by sometimes replacing ithers with plus, tuples with multiplication, and so on. Now, there is one more important thing that we will need is that if two things are isomorphic, then we can replace them in any functorial context, meaning that if you have some type that contains an a inside of it, and you have some other types that, or rather the same types that contains a b in that position, basically you have like a functor, and it's applied. If a is isomorphic to b, then f of a is going to be isomorphic to f of b, as long as f is a functor, any kind of functor, including phantom, covariant, contravariant, phantom, you name it. And the proof is very easy. We just take our isomorphism and we apply map to it. And by equational reasoning, we can prove that those things are actually isomorphisms. Yeah.
Where does this term phantom functor come from?
So phantom functors are those that do not actually contain any value with it. So they take a type, but they don't contain any values of that type, which means that you can change that type arbitrarily, pretty much. And essentially at runtime, regardless of the type, like no matter what your type is, you're going to have the same exact representation of your data. So an example of a phantom functor is const a, right, which contains only one value of type a. So const ab doesn't contain any values of type b, but only one value of type a, which means that you can take const ab and convert it to any other const ac just by unwrapping and rewrapping the value. Okay, and one more thing. Scala is a little bit too verbose for me, so I'm going to be using like nothing comes up a lot, and I'm going to be using just the bottom symbol for nothing. Okay, now let's talk recursion. So let's say we have a list. A list has two cases, nil and cons, right? And it's basically the same thing in Haskell, except like not as verbose. And we would like to fold over it, right? The reason we want to look at fold specifically is because fold is the essence of recursion. Every single function that you can write on lists, you can write using that one function. You can write zip, you can write map, you can write anything. So over here, for example, I have map, sum, and like is empty, and all of them are implemented in terms of foldr. Zip is a little bit trickier, but basically you're going to be folding and returning a function that takes another list rather than, so you basically do two folds. You fold one time and you return a function that is going to take another list and zip it. So you sort of like you have to partially apply it to the first argument. Or let's look at a more realistic example, right? In a functional programming, we often deal with trees because our representations of data correspond to, to the actual semantics of our data, and so they are represented as trees. So here's an example of a tree for, say, just expressions in some language. Very simple. And once again, we can write our foldr, although you normally would just call it fold in this particular case because foldl doesn't really make sense. And similarly to the list case, we can also implement all sorts of functions. For example, we can evaluate our expressions, or we can print them, and all of that is taken care of by foldr. And in some sense, we are reinterpreting our recursive data structure into a different type. So think about this as a change in representation, or possibly with normalization. Like we might be losing some information, but we're definitely not gaining any. Now let's look at the type of foldr in more detail. What does it look like? Well, since we're in Scala, functions are by default not curried, right? So that's why I have tuples there. And we first are going to use pairing. Remember pairing? The idea is that if you have multiple functions that return the same result, you can combine them, but you have to. So if you have a function from A to B and another function from C to B, you can convert them into functions that takes either one of those two arguments and returns a B. And so here's the same idea, right? We have three functions, and we're going to convert them into a single function that takes either one of those arguments. Now, if we look at this representation at this type, and we'll discuss both of these concepts later, but basically there are two important pieces here. One is called like a pattern or a signature functor, and the other one is called algebra. So let's talk algebras. In mathematics, an algebra is basically a set together with some operations on that set. Often we also have certain laws, or say normally you require conditions that no matter what operations you apply to your elements, you're going to stay in the same set. So operations are closed. In category theory, there's also a thing called algebra, but this time it's called F-algebra. And the main difference is that in category theory, instead of expressing things as a sort of a list of operations, you have a single pattern functor or signature functor that corresponds to all of those operations simultaneously. And we'll see exactly how they map one to another. So this is in category theory. We have a thing called F-algebra. And an F-algebra takes a functor and a carrier of the algebra. Basically, it takes an f of c and returns a c. So what does it mean? Well, if you imagine that f represents your operation, all possible operations, right? So it's essentially like a co-product of possible operations where the arguments of those operations are replaced by c, right? So it could be, for example, a plus b, or it could be like a multiplied by b, where a and b are both your carrier object, or carrier type in this particular case. And the idea is that an algebra is basically a way to reduce information. Like you take those operations and you, with their arguments replaced by c, and you somehow combine those arguments together in any way you want. So let's define the signature functors then. The idea is that a signature functor, remember, it corresponds to all possible operations. Right? In this particular case, we have 3 operations. One is a literal number, meaning that it doesn't take any arguments that are members of this. Like it doesn't take any recursive arguments. We are not trying to. It only takes an int. There is no recursion there in the literal value. Whereas add, right, takes 2 arguments that belong to the carrier set of our algebra. Does it make sense? And so we have arrived at recursion schemes, right? And it didn't take us too long. We basically started with foldr and we applied pairing, and then we extracted one type, and that's it. We are already at recursion schemes. So, well, the first thing is that if you're familiar with recursion schemes, you've heard the word algebra and you've seen that type signature, right? But we'll see that this word algebra occurs in so many contexts in functional programming. And so we're going to explore other ways and other cases where it occurs, and we'll show that they're exactly the same. It's the same exact concept. So, but first, let's talk recursion schemes. Recursion schemes, very simple idea. If you have a recursive data structure, let's just extract one layer of that data structure. Imagine that you have a tree, and you take the root of that tree, and you sort of pull it out, and you separate it from its children. That's what a single layer is, right? It's just that top element separated from its children. So in some sense, for every recursive occurrence of a type, expr, right? We leave a spot for it to be filled in. And you can immediately see that this is very similar to what in F-algebra the signature functor is, right? It also represents all possible operations that we can do with our trees. Now, furthermore, in recursion schemes, we normally have this to functions project and embed, which allow us to extract that one layer at a time. So if we have an expression, we can pull the top layer out and we get x per f of expressions. Right? We still have those subtrees. They're just right below our layer, but we've separated it out. And in a similar fashion, we can also embed things, meaning that we take a single layer with some subtrees underneath it, and we say, oh, we're just going to combine them back together. Now, what is this? Okay, so now we can use this on the previous slide. They have it? Yeah, so I forgot to mention, but our fold can be expressed in terms of algebra now, right? The first argument there is algebra, meaning that it's a function that takes a signature functor with some carrier, z, right, and returns a z. And we can use it to fold one layer at a time. And the idea is that we start at the very bottom of our tree, and we reduce sort of like from bottom up. We reduce our tree bottom up. Yes, towards the root. And at the end, once we're done, we end up with a single value of type z. And now we can use those two functions, project and embed, to rewrite foldrs as a, well, arguably a simpler expression, although you might disagree. Essentially, the idea is that there are 3 steps here. We first project, meaning that we extract one layer, then we map over it, and we reduce all of its children. Then we end up with just one layer, and everything below it is already reduced. And then we apply algebra once again to reduce the root node. Yep.
Should we foldr rs inside?
Yes. Over here, it should be foldr rs. That's fold rs. Now, recursion schemes goes a little bit further, where they actually have a type class called recursive. And another, so recursive contains your project function, basically allows you to extract one layer at a time. And there is also a type class called co-recursive that allows you to embed one layer at a time. And everything else on those type classes is a derived operation. And there is, in recursion schemes, there are all sorts of combinators. But all of them, conceptually, they follow from this idea. If you can extract one layer at a time and you can work with one layer at a time, then you can do all sorts of things in a general fashion. Now, remember we had this evaluation and printing, right? We had 2 ways to reinterpret our expressions. Well, we can do that with recursion schemes as well. It's just a different way of writing the same exact thing, right? When we were using foldr, we were just, it was sort of like inline. But here we've separated the algebra, and we have like the algebra separately from folding. Okay, now let's go back to the types, right? Once again, we do pairing. We get to this representation, but what if, instead of extracting the pattern functor, what if we extracted the algebra? Like the entire thing. Look at it. It's 3 functions. It's a record of 3 functions, right? Or, well, it's a tuple, technically, but a natural representation for it would be a record, right? So we've extracted our algebra. What does this remind you of? Well, church encoding is close, but not exactly. We'll see church encoding later. Yeah. Yeah. like finally tagless or final tagless, depending, or tagless finally. Many different ways to say that. But, or you could say, well, that reminds me of type classes. Or just, yeah, I think that if you are more familiar with Scala, you would probably say final tagless. If you're more familiar with Haskell, you might think, oh, this is just a class, right? It's just a type class. And so now our type looks like this, our foldr. And in Scala, we have essentially, we can pass dictionaries both explicitly and implicitly. And in this particular case, I'm passing this dictionary explicitly. But this is an isomorphic expression to what we had before. So it's just a different way of writing fold. Right? We started with foldr. We got to foldrs by extracting the pattern functor. Now we extracted the algebra itself as a dictionary, and we get yet another representation of foldr. And this one follows the same pattern. Like whenever we encounter an expression, we first reduce its children, and then we apply algebra to the root. Now, one reason to do this is because this does not allocate, and potentially does not allocate at all. Because here, before, when we had recursion schemes, our foldrs allocates stuff, right? Because it has to pass a pattern functor to our algebra. It has to allocate intermediate nodes, which are going to be immediately discarded. Whereas this version potentially does not allocate at all, because it just doesn't need to. It's just you're passing values of z, right, our carrier, around directly. And by the way, there should be a type parameter over here, but okay, now in the same thing applies, right? We can again write print and eval, as they look slightly different, but it's the same idea, right? It's just a different representation of folding. Now, and this is what is called final tagless. And except that normally in Haskell, say, final tagless is used with type classes, whereas here we are passing dictionaries directly. But we could pass it as a type class. And now we have like a fold in, like that is perhaps more familiar to people from Haskell, final tagless in Haskell. And once again, we implement our type class instances. And once again, we have the same exact thing, right? We can print and eval. And we got all of that just by transforming foldr in different ways. So all of those techniques, all of these techniques is just a different interpretation of the same idea. The fundamental idea here is that you want to recurse over a data structure. The rest is just an overhyped technique, or one of them. Now, yes. Okay, so every function can be expressed in terms of fold. What does it tell us? Like, if I can give you a fold, the signature of a fold, and you can express every single function on that type, what does it tell you? Hmm?
That always goes back.
Sorry.
It's isomorphic.
Yes. Fold is isomorphic to the data structure itself. Now, if you remember yesterday's talk, right, we looked at Yoneda embedding, Yoneda lemma, right? And there we showed that F-map is isomorphic to the data structure itself. And here it turns out that fold is also isomorphic to the data structure itself. And this is known as Boehm, and by the way, I might be butchering the name, so just keep that in mind. I have no idea how to pronounce it. So I'm going to call it Boehm-Beredici, whatever. And sometimes people think of it as church encoding, although that's incorrect. It's like colloquially known as church encoding. And the idea here is that, well, if we can express every single operation in terms of fold, then it doesn't matter whether we get a fold or the data structure itself, right? In fact, we can take our fold and we can pass type constructors into the fold. Think like, what is fold R on list? Fold R, empty list, cons. It's just an identity, right? So we can go in both directions. If we have a representation in terms of fold, we can go back to the data type itself. And if we have a data type, we have a fold. Now, so we had this type. But the only problem is that this, for all z, it occurs too early. Like, we don't want to fix z too soon, because it doesn't really occur in expr, right? So we are going to move it a little bit, and it turns out that now we have an isomorphism. And all of this are like different variations on Boehm-Beredici encoding. I mean, maybe there is one canonical, maybe one of them is canonical, but or rather, you know, by definition, one of them is the Boehm-Beredici encoding, but it doesn't really matter. And in fact, we can explicitly construct this isomorphism. So if we have an algebra, we have an algebra and a fold, right? We have like the second type, right? The second value is essentially like for all z, it's just the right-hand side, just one of those, right? Expressed as a single type. Unfortunately, in Scala, we do not have polymorphic values or polymorphic functions, so you have to encode them as a dictionary. And then in order to convert in one direction, you essentially just provide a fold, and to convert in the other direction, you provide data constructors to that fold. And in mathematics, there is a thing called initial algebra. So if you have an F-algebra, there is something like if you have a monoid, right? Monoid type class, you know what a free monoid is, right? Does everybody know what a free monoid is? Sort of, right? Well, the idea is that we want monoids are not exactly is not exactly the best example because monoids have laws, but you know, we can come up with a free monoid, meaning that it's a kind of like a monoid that doesn't really know how to reduce things. It only knows, like, monoids have composition, right, and identity. Identity has to satisfy certain laws. Composition has to satisfy certain laws. But a free monoid does not do anything apart from reducing your expressions according to those laws. So, for example, if you add, sort of like in free monoid, if you add a to b, it's not going to reduce, it's not going to look inside of your values of a and b. and somehow combines them together. It just doesn't know about it. It's kind of like free of extra assumptions. And initial algebra is roughly the same idea. If we have an algebra, or rather, there is actually a category of algebras where morphisms are algebra homomorphisms. And the initial object is called the initial algebra, right? But the idea is that, what is an algebra? First of all, let's remember, it's a functor that is fixed. It's a morphism from FC to C, and it's a carrier set. Now, the two things there are not fixed, C and the morphism. Those are the part of this category. And your initial object, usually when people say initial algebra, they mean the carrier of the initial algebra. And I won't go into too much detail on this, but basically expr is the initial algebra, well, is a carrier of the initial algebra for expr A, or like expr F of, like for the pattern functor expr F. But the important, I think, takeaway from this part is that every type, like Bowen-Berardischi encoding, right? It's a very important idea because it tells us that things that a recursive type can be represented in this way, and that this is an isomorphism. And furthermore, there is something else going on here, which is that, and by the way, don't take this literally. This is not like, we're not doing math right now. We're talking intuition, right? So don't take it completely literally. But essentially, every type is isomorphic to the things that you can observe about that type. In the case of a recursive object, recursive type, the only thing we can observe is its fold operation. Like, it's expressible in terms of fold. So folding, since the only information that, like, we can get all of the information about that type by folding, that means that it's isomorphic to the fold itself. And it's kind of seems to be a little bit connected to Yoneda lemma, but I haven't really explored the connection in full detail. And and you can, again, like, intuitively prove it to yourself. You can say, well, how about I make all possible observations about some object? Like, I write down every single thing I know about it. Then, if I can distinguish, like, I'm going to end up with a tuple of every single observation, basically. Imagine that observations are Booleans, let's say. Right? It's a giant Boolean. And if I compare two objects, and they are equal, then this tuple of observations is going to be the same. On the other hand, if I compare my tuple of observations, if there is at least one element that is different, then I'll know that the original objects are different. So that's, like, that's where you sort of have an isomorphism between those two representations. I'm sort of, it's not exactly maybe, rigorous, but it's definitely true. Intuitively, it makes sense. Okay. Now, let's talk about free monads, right? I promised you that it's not just going to be about final tagless recursion schemes. It's also going to be about free monads and MTL and so on. So, a free monad, right? We talked just a little bit about free monoids. Free monad is a very similar construct in some sense. It's a monad that is free from any assumptions. meaning that essentially it represents just a sequence of operations. It doesn't know how to reduce those operations. It doesn't know how to run those operations. All it knows about is that those operations must satisfy the monad laws, meaning that things are associative, meaning that in your sequence, the structure doesn't really matter. The sequence matters. And that you have pure, or like an identity natural transformation, pure. And that pure also satisfies certain things. Like it can reduce pure, but it cannot reduce anything else. So it's sort of like a free computation, free sequential computation. Now, the way we usually represent those in Scala and, well, one way to represent it in Haskell. Like in Scala, this is not a very good representation because Scala does not have laziness. And so this representation is going to limit you to only finite sequences of expressions. So you cannot have like recursion. But nevertheless, it's still a valuable way of looking at it. Basically, we have two possibilities. It's either a free monad value is either a pure value or a computation that is suspended inside of some f. And the suspension means that we have the rest of the computation inside of f, but before we can get to it, we have to run the f on the outside. And you can think of it like if basically if we nest suspend instead of suspend instead of suspend and so on, we're going to get f inside of f, which is exactly what it means to have like a sequence of operations. You extract, you have an f on the outside, you run it, you extract the inner layer, you run z, you extract the inner layer of z, and so on, until you hit pure at the very, very end. Or not, depending on, maybe you have a recursive structures there. Now, the reason people use free monads is because they want to suspend, they want to write codes that can be interpreted in many different ways. Now, think back to our data structures. Why do we have fold? Why do we have like recursion schemes? To interpret data structures in different ways, right? The same idea here. We want to interpret our code, our sequentially composed sequence of operations in many different ways. So let's take a look at a very simple API of sorts. And by the way, this unit means side effects, right? But we're not going to have side effects once we get to free monads. Just for you to understand like the structure of it, right? We have get, which takes a key and returns a value at that index, let's just say. And we have a set that takes an index and a value and sets that index to that value. Now, using free, we can write a program that looks like this, where get and set, they're sort of like, I'm not entirely sure if I have it. Oh, yes, I do. OK, so we're going to talk about set and get in a little bit. But basically, you write an expression like that, right? A function like that. And it expresses a program that is first going to get the first element, then set it to the old value plus 1, and set the second element to that value plus 1. And then once we have this expression, free monads allow us to reinterpret it in different ways. We just need to write an interpreter that is going to take every single, remember, free monad consists of layers of f, where f is our service f. And we're going to talk about how it looks like. But basically, it's layers within layers of that type. And if you want to run it, you supply it with a way to transform every layer into your target monad. In this particular case, IO. And there shouldn't be type parameter here. Or, it can also be reinterpreted in other monads. For example, state. You might not want to run, like in production, you're probably going to be running in I/O. But during testing, you might want to run in state monad so that everything is pure and you don't actually perform side effects. Now, you're probably familiar with so-called freer monads. However, regular free monads require F to be a functor. There is this requirement which makes the signature a little bit more complicated. Basically, in order to make this a functor, service F, we have to do some extra stuff here. We have to sort of like, we are going to be constructing, right, a sequence of service F nested within each other, right? And the problem is that in order to nest things, you need some place to put them, right? Just like a list. So think of this as a sort of list where this is your tail, A. Or rather, it's kind of like a layer of a recursive data structure. Remember X per F, it had holes for subtrees, right? Or sub-expressions. The same thing here. We have a hole here for the rest of the computation. And we can fill that hole with further service F operations or like free, whatever we want. And now, in order to actually write things using free monad, we need some helper functions, which basically just suspend, like add a single layer to our. Basically, they represent a single layer operation. Like get is just an operation that is, like it's a data structure that consists of get, and then it's gonna, in its continuation, sort of like this part, its tail, right? It's just pure, meaning that it's just gonna take a value and return it. It doesn't do anything with it. And then we can write an interpreter, right? And my interpreter is partial, and I'm not sorry, because this interface cannot be satisfied. Well, it can be satisfied, obviously, by a total function. But since we are sort of representing this idea of storage of like an array of data, right? It's probably going to be finite. And so normally you would do something better than this, or not. It depends on, like certain things in function programming you just cannot prove. Like there are certain invariants that are kind of have to be asserted. This is not one of those cases, but it's a slide. Now, usually people use freer monads. Now, freer monads are cool because they make our boilerplate a little bit easier, although not easier to understand, just easier to write. And the difference is that we have this flat map, a new constructor there, right? And basically that flat map is going to take care of sequencing things, right? Before, we were basically putting F inside of F inside of F and so on, right? But here we're going to be using flat map to construct our sequence of operations, right? So it's instead of a like nested Fs, we're going to have essentially a tree consisting of flat map operations where leaves are suspended computations. And this part becomes easier, right? We don't have that like tail. We don't need a hole to fill in with data because we have flat map, and that's gonna sort of like represent the composition. And the interpreter looks exactly the same, except that there are some slight differences, but they are not essential. Now remember the statement I made, that every type is isomorphic to the things that we can observe about that type. Once again, a disclaimer, might not be exactly true, but that's intuitively true. And like under normal circumstances, if you apply this principle, you're not going to run into any problems. In fact, we're going to apply it to free. Now, the only operation that is allowed on free values, or should be allowed on free values, is run free. What is run free? Well, if we go back, oops. Oh, yes. Okay, so I had this run free over there with a signature, right? And the idea is that free represents a computation where f is not interpreted. Like f is not, like we have a sequence of f's nested, right? But we don't actually assign meaning to it. We just keep them around, all of those f's. Whereas run free essentially takes that entire structure and it reduces it. Think foldr. What does foldr do? It kind of like takes your entire structure and reduces it down to one value. Run free, or maybe sometimes it's called like foldm, fold free, I don't know, like many different names. The signature is more important than the name. It basically takes a natural transformation from f, like you have to give it away, give it a function to transform every single layer into some other representations that you can actually reduce. So the way we're going to be reducing those layers is, we also have this monad constraint. That's what we're going to be using in order to merge the layers together. So, well, what about this representation of a free monad? We've reduced it down to bare minimum. It doesn't have anything extra in it. It does not allow you to do, you cannot observe any structure, except the only thing you can do is run free. And by the way, this is going to be more efficient than any other representation in Scala. I'm not entirely sure about Haskell, but I'm sure that the compiler is not that smart. There is a reason why people come up with new free libraries for free monads, is because all of them are slow. But if you write it like this is going to be fast. And notice that I haven't really defined monad here, but it's just a simple exercise to define it in this particular case. Essentially, in your monads, that's where you're going to be creating like some in-memory representation of the data. Because you're still going to be allocating some stuff, right? Because you still need to allocate that trait, or like think of it as a dictionary. But that's about it, right? You don't have like, I take it back. It might be still slow. It's just like life is hard with free monads, Things are slow. Allocations kill everything, So, and like if you try to implement all of those instances, everything just works out. Just a little bit. It's kind of like type golf. Is everybody familiar with the term type golf? Yeah. So you just fill in the holes and things just work out. Okay. Now let's take a look at the type. Now I took some liberty to convert type classes into just regular traits. Over here we have a normal arrow because types do not care. So, and let's look at this term in particular, right? As a natural transformation. this natural transformation here, this term, this type here, it can be rewritten in such a way that it takes G as a parameter. So it's going to be a constraint on G, right? So a natural transformation, right? This is a type. Imagine that I come up with a like a new type, A of G, such that it looks like this. So it's just a natural transformation, but the only parameter in that natural transformation is now this G. Because F is sort of fixed instead of free, right? So what is A? Actually, any ideas, maybe ahead of time? Yes, it's also called algebra, the same word again. So consider this a case of service F. What is our natural transformation? Well, again, it's Scala, but a natural transformation is basically something that takes a type parameter, and then for all fx, this part, returns you a g of x, right? So let's look at its type in more detail. Now, this part is going to be tricky. I'm not going to lie. Because here we have a GADT. Now, if it was a functor, like we sort of went to freer monads, right? And this is a nasty type because it's not an ADT. ADTs are simpler, but nevertheless, you'll have to sort of imagine that there is a type that represents equality between types, right? This x equals int. And basically, this case, because it's a GADT, it does not only contain a key, but it also contains a proof that the type is int. So it's kind of like a combination of two things here. But this part is normally erased. Like, you don't see it. It's there. Like, if you read the documentation for GADTs, it actually explains, in, like Haskell's documentation, it actually explains that they can be also represented as regular ADTs that take type equalities as parameters, like implicitly take type equalities as parameters. Which, if you ever try to deserialize an ADT, that makes life very painful. Like, ADTs are fine. GADTs, very easy to serialize, but pretty much, like, before you, like, as you're deserializing, you have to decide on the type. You cannot decide on the type ahead of time. Basically, that's the problem with GADTs. Anyway, and so the idea here is that this can be represented as a pair of a key int and the proof term that x is int. And the same thing for the second argument. Now, we're going to, actually, this is unpairing, right? We're unpairing it. Because it takes a pair of two types. Not a pair, an either of two types, right? And we're going to convert it into two functions. Each of them takes one type separately, one of the cases separately. Basically, we sort of do, we kind of like pattern match on this either, right? We split it into two cases.
Should that be a comma or also an
You mean here, this one?
Yeah.
Yes, this should be a comma. Because essentially, we either take this argument, like this function, right? It takes either one of these two. It returns a g of x. So we convert, The only things that it can do with its argument is pattern match in it. So there are going to be two separate cases, one corresponding to one to the left and one corresponding to the right. So we are just basically splitting it into those two cases. Now, in this talk, we haven't talked about distributing universal quantification over inside of tuples, but it still works. Like one day did not make a difference. But for those of you who didn't go to my talk yesterday, basically, it can be proven very easily for tuples that you can distribute like that. And it's just a case of typeclass, except that you might want to do that in Idris, just so that your quantification can be made explicit, and so that you can explicitly pass types around. Now, another interesting thing about type equalities is that if somebody passes you an x equals int, you know that x must be int. And that's the only case where this works, right? So if you take an x equals int as a parameter, you might as well just say, I'm only taking ints. And so this is isomorphic into g of int, right? We just took this part. We sort of like said, well, if somebody gives us this thing, then it must be the case that x is int. Therefore, we are going to substitute int instead of x everywhere. And in the second case, the same thing applies with unit. In fact, this is actually also a Yoneda lemma. It's just a different version of Yoneda. And so if you look at this type, what does it look like? It looks like a record of two functions. And in fact, this record. Now, if you know MTL, you might be like thinking, oh, that looks familiar. If you know MTL, like final tagless, any one of those techniques, right? This is just what we call like an algebra in, I guess not in MTL, but in final tagless. In MTL, it's just like a type class. I don't know. What do people call such things in MTL? I mean, in MTL, you would also combine it with a monad constraint, right? You would have like monad service instead of service itself. But that's also an argument that we are getting in our run free, right? So we could, in principle, combine them together. Now that we know that it's just a record of functions, two records of functions can be combined together. And so we can rewrite our free monads in a new and different way, right? Before we had this natural transformation, and we were taking a functor over here as a parameter, and now we're going to take an algebra as a parameter, as a type parameter, and an algebra as an argument. And that's exactly what final tagless is, because if you look at just this part, this function alone, that's exactly what we mean by final tagless, right? Except that normally we pass things implicitly. And so if we have a program like this, and let's go back once again, the main, like, focus on this signature alone, right? It takes a G with a constrained monad and an algebra of G, right? So if we have a program like this, we might as well discard that wrapper around it and just rewrite it as a program that takes a G, monad, and an algebra, right? We don't need like an extra wrapper around it. And so suddenly we've come up with final tagless, right? But what if we make a type class out of it? It also works out. So what's the takeaway? Well, first of all, that everybody's lying to you. I mean, not lying precisely, but more like confusing you. Because really what you should care about is not one particular technique. What you should care about is what is the meaning of the codes that you write. It doesn't matter whether you use free, freer, polysemy, or like F, or MTL, final tagless, whatever. The most important thing is that you want to abstract over operations and you want to sequence them. That's the core idea. And the fact that we know that all of those representations are actually isomorphic. Like we can prove that there is a mapping in both directions. If you write me a program in one representation, I'll be able to mechanically transform it into the other. And so to sum it up, like we've talked about a little bit about identity of indiscernibles and its connection to isomorphisms, type algebras, and then we showed that folds are essentially just recursion schemes and essentially just final tagless. And you can come up with so many different encodings. You can take monoid and you can convert it into a dictionary. You can then create a pattern functor for monoids, right? And then we also talked about Bohm-Berardinci encoding, which is a very powerful idea, I think, which is that things are isomorphic to their observable properties in some sense. And we talked about free and final tagless. And that's about it. So thank you for listening. And now it's time for any questions that are left. Yeah.
Yeah, so this is great. Thank you. It's awesome. So now we know the three equivalent ways of writing a program. Since we know, now we want to write a program, we know they're all equal. But what are the considerations to say I'm going to write this way versus write that?
Well, personally, I prefer, I guess, final tagless or MTL, but mostly because there is a good reason to avoid free monads, in my opinion, is because so the way people usually compose things using free monads is using coproducts. Because if you think about it like the pairing stuff, right? It takes some things that we have a function that takes a coproduct, like either one argument or the other, and then converts it into tuple, which takes, so it kind of like changes the representation, right? And that fundamentally affects how we compose effects. Because if our effects are coproducts, then we have to compose them as coproducts. If they are products, then we have to compose them as products. Now, composition of products is basically just pass both things at the same time, right? If you want to write a program that uses functionality from two different algebras, you just pass both algebras. Whereas if you want to write a program that is expressed in terms of two different pattern functors, you have to take a coproduct of those. And coproducts, they come with a cost because you have to like embed your operations inside of a coproduct. It's kind of like not as easy as passing two arguments to a function.
So that's a reason to go with final tagless versus
Yes.
free monads.
Yes.
What about recursion schemes?
I think that recursion schemes are great for many, it's kind of like a nice way of looking at things, but I feel like even with recursion schemes, I would mostly go for final tagless. However, the code, recursion schemes are more general in some sense because the fact that you've separated that pattern functor out actually allows you to write a lot of very general code. So like recursion schemes have a ton of combinators, right? And for all sorts of purposes. They are all based on this one idea, like extracting one letter at a time. But there is so much so many combinators that are related to recursion schemes. So if you are looking for some, like a powerful tool to express those recursive computations specifically, then go with recursion schemes. If you are looking for a way to express sorry, I'm thinking about like why would you even go with final tagless in this particular case? There is a reason. I mean, in Scala, it's definitely a lot easier to work with. Recursion schemes generally like are not very nice. So there could be a lot of different considerations here, like depending on the language, depending on like your performance requirements, depending on your, you know, like how much you are willing to, how much boilerplate you're willing to write. Like final tagless usually comes with pretty much zero boilerplate, except that if you are passing dictionaries implicitly, then you need new types. But other than that, it's pretty easy. In one moment.
So one question that might help you, I don't know. If you're, sorry for asking another question.
No, it's fine.
If you're extending a language, is it going to be easier? If you haven't decided, in the final form you're just so you can iterate.
I think that, honestly, I think that final tagless would be easier to extend, a lot easier to extend. Yeah.
So just off from your comments about
Mm-hmm.
in category, sure, yeah, so the categorification works well weird. So talk about this from 1960s, weird theory.
Mm-hmm.
Yeah, common idea, and category theory, and it was proven that the weird theories correspond to fundamental monads on set of these So one of the aspects of the weird theories that make it easier to work with monads is that you freely compose the weird theories using coproducts. So
Mm-hmm.
one theory is the theory one, and another theory is the theory groups, which come with their equations. You use a coproduct in categorical weird theory to create a composite weird theory that includes both
Mm-hmm.
equations, right? And the MTL style kind of aligns with that because in your dictionary you have operations, although in the MTL style is typically parameterized for some effect. But what I often find myself doing is coming up with an instance of, say, like I'll do my error type error is equivalent to the limit ask functor raise or something.
Mm-hmm. Mm-hmm.
I'm just going to freely compose. So in a way, I think of that as a co-product as well. Co-product here.
Right. Right. I mean, I think the right way to think about, like the co-product distinction is not very important, right? It is important practically, but it's not theoretically in this particular case. I mean, in both cases, you are like combining things together, let's just say, right? Whether you combine them as a co-products or products makes, mm-hmm. Yeah.
You showed that you started with folds, and also you mentioned that you were recursion schemes.
Yes.
But recursion schemes, as you mentioned, tons of combinators, and some of them actually go with unfold, like high or those things. And I fail to understand how this
Aha.
organization can invent these
Yes.
new ones.
Yes. So there is, let's just say that there is an unfinished piece of, this is something that I want to explore in more detail. But essentially what you do in order to bridge the gap between combinators on recursion schemes and combinators on algebras is that you need to add an extra type parameter to all of your algebras. So that instead of taking f, at least that's my intuition. So instead of having like an algebra fz to z, right, or just like a, like a dictionary like this, where is it? Oh. Let's go back to the first half. Okay. Yeah, perfect. So you see over here, we are taking z on both sides, right? We're taking z and returning z. Well, in a lot of like recursion schemes are based on this more like generalized algebras, which may take something else as an input and produce something else as an, like different things as input and as output. So what you would want to do is to add an extra type parameter here. So let's say one type parameter like f from and to, and then you take values of type f and you return the values of type t, right? And in fact, if you do that, you can derive a lot of interesting stuff. But it's I haven't gone through the whole process of deriving like high-low morphisms and stuff like that. I'm sure that it is possible, but I'm not like haven't done it yet. Let's just say. Any other questions? Yeah. Oh, go ahead.
So I've seen use of like sometimes just as you use free, code free, you have used in case where you want to represent where you have a tag at each level and recursively nesting. Have you seen examples where you have algebras that combine both code free and free together?
Is it combine free and co-free?
Yeah.
No, not really. So one thing about algebras is that they have a certain shape. Let's just say like if you look at them, they have a functor on the left side, right? F z to z, and that's very important because that means that you are kind of like, you're not making an observation about your data, if that makes sense. And that's where, like if you have co-free, that's the opposite, where you are, the main thing about your data is that you can make like different types of observation about it. Free is all about like when you compose things together. So instead of, basically, co-algebras are those where you kind of like can take an object and decompose it in some way. So we have a z to f of z. And algebras are those where you take an f of z and you combine it somehow into z, right? And the combination of those would have both operations, right? It would have some operations that like decompose and some operations that compose. But then you run into, like tricky problems like, well, imagine that I added an extra constructor to my x per c that was taking a z and returning an int, right? But now, how do I make a free structure that does that? I have to somehow like figure out where to get that int from, and that is the tricky part because I can both construct. So like I construct a lid of 10. And then I call my function that extracts an int. What is it going to return, right? So in that sense, I haven't seen any way to like combine them together in that sense.
Probably would have to be across different type parameters or something.
Maybe, yes. Any other questions?
Do we have any slides?
Oh yes. Slides are actually in room A108 on Slack. And also in the room isomorphic reasoning on Slack as well. Okay, well, thank you all for coming and thank you all for listening. Yeah.